Great. Claudio, please.
Okay, first of all, don't worry, they're not two talks, it's one that we split. We are Claudio Codella and Nadia Balucani. We are talking on behalf of a group coordinated by Cecilia Ceccarelli. We prepared chapter 11 with the help of a lot of people that I'm here listing. Dominique Bockelee-Morvan, Eric Herbst, Charlotte Vastel, Paola Caselli, Cecile Favre, Bertrand Lefloch, Karin Oberg, and Satoshi Yamamoto. Okay, and we would like to thank the scientific organizers and the local organizers to make this finally possible after all these tough years. So, sorry for the 30-second spans on that, but I guess that's very important. So, can I, like the rock star? Yes. I would like to why we are here. Okay, we are talking about star formation. So we say, so what? We here I summarize that the process of star forming regions. So we were clouds, okay, molecular clouds that at the end with a lot of verbs in the middle. So accreting, rotating, and falling, bursting. At the end, you know better than me that the final process of this formation is the formation of a sun-like star, because we are talking about a sun-like star, and the protoplanetary system. Okay, fine. So you say, and so what? But well, we would like to add something more, because we would like to say that simultaneously with the process of the physical processes leading to a sun, there were also a lot of chemical processes that made us. Okay, they made our eyes, they made our heart. With the bricks that we are inside, there were in a molecular cloud. We were a molecular cloud. So that's amazing for me. That's this amazing question, fantastic issue. And only with the collaboration between astronomers and chemists, this can be studied. So I'm an astronomer, but I'm not a chemist. I need a chemist. Here we have Nadia Balucani, alias Miss Heisenberg for Breaking Bad people.
Thank you, Claudio. Okay, so my name is Nadia and I'm a chemist. Sorry, I'm not an astronomer, so I hope I will keep it clear and simple, let's say, for all of you. So let me start by saying, why do we care so much about seeing organic compounds in space to begin with? Well, there are reasons actually for that, because organic compounds are at the base of all terrestrial forms of life, and the point is that there is no obvious way of how these compounds have been synthesized. Well, not now. Now life is on, and of course photosynthesis can convert most of oxidized carbon in reduced carbon, and organic compounds life is made of reduced carbon compounds. But the question is, how did it start? So is this obvious in this way? Well, it's not obvious at all, and you can appreciate by comparing the elemental composition of our galaxy, our planet, and the elemental composition of a human body. As you can see there, in many cases, actually, the main components of a human body are reduced compounds of oxygen, carbon, and nitrogen. That means also a lot of hydrogen, of course. And we are, in a way, more similar. Our composition is more similar to that of the galaxies rather than to the composition of our own planet. And so, in a way, we might consider ourselves reduced carbon-based entities like aliens in the planet where we stay. Well, it's a kind of a joke, but not really a joke, because, as I said, it's not obvious at all how this reduced organic chemistry started in the absence of life. Now it's obvious. It's a non-equilibrium chemistry kept the way it is by photosynthesis. But how it started, we really don't know. And so it's kind of intriguing to see that yes, in space, most of the molecules are kind of simple, reduced carbon, like methane, yes, but it's not really interesting for, to think of prebiotic chemistry leading to life. And indeed, the elemental composition is similar, but then the molecules are completely different. So it's a kind of really interesting to see these molecules, organic molecules with some complexity, not the necessary complexity, but it's really interesting. Here you see typical biomolecules, that's a segment of DNA, and the other one is a protein, a very complex protein, that's gluten actually, maybe you have a problem with it. So these are the typical structures of molecules of life. And so how do we go from very simple species in the galaxies up to these complex molecules? So that's at the base of so-called prebiotic chemistry. And as I said, seeing these kind of molecules, and now we have seen roughly 290 molecules in interstellar and circumstellar regions, and 45 of them are actually contain carbon atoms and show some complexity. Of course, they are not really as complex as we need, but they do have all the functional groups which are necessary for biomolecules. And we can see an example in this list where we do have a formamide with a peptide bond, cyanoacetylene, nitriles unsaturated nitriles are very famous to have the capability of evolving into real biomolecules. And so as a chemist myself, I wonder how these molecules can form in the conditions of the interstellar medium, which are really bad if you think of chemical complexity because of the very low number density and the low temperature. These are not favorable conditions for chemistry. Of course, to understand the chemistry which is behind the formation of these species, we need a multidisciplinary approach. This is why it's so important to interact with my colleagues astronomers. And first of all, we have, of course, astronomical detection. Astronomical detection are baked by astrochemical models. And in astrochemical models, you must consider both the physical parameters of the objects you are investigating, of the region of the space you are investigating, but there is also a very complex chemical scheme inside these astrochemical models. And I have to say that among the many reactions which are included in all standard models, only a small percentage has been really investigated in laboratory experiments or quantum simulation. And there is a reason for that. It's very difficult to reproduce the harsh conditions of the interstellar medium in lab experiments. I am an experimentalist, I can tell you. So that's very important also to rely on a quantum chemical approach, because that helps in all cases where you don't have the chance to really investigate the species. Okay, so what's the state of the art about our comprehension of these processes? Well, there are some parts of this global scheme, of this global vision, for which there is a common consensus, and other parts which are a little bit more debated. So let's briefly describe them. Of course, I'm giving here only just just some pieces of information, and I invite you to read the book, of course, to have a detailed description of all these processes that I'm very quickly mentioning here. Okay, the consensus, as I said, regards the formation of icy mantles on interstellar grains, because, of course, during the prestellar core phase, during the cold cloud phase, we have plenty of radicals and simple species, atomic species, impinging on the dust grains. And, of course, because of the low temperature, they keep on the surface and they can recombine. So in this way, you easily produce hydrogenated species, also some oxygenated species, because oxygen is relatively abundant. And then you form this mantle of ice. The main component of this ice is water. After that, you might have even the landing of some species which are able to react with the water molecules in the ice. And so you form a small set of molecules, but which are very important, because these are going to be the bricks to form more complex species. After this stage, there are actually two scenarios. Both are considered, and there is some debate on the relative importance. Probably, of course, both of them will be active. So on one side, you can imagine that these molecules synthesized formed in the mantle will go to the gas phase by sublimating somehow, and then they keep on reacting in the gas phase, producing other species. But there is an alternative explanation, that is some species in the mantle can be converted to radicals. Radicals are very reactive species, not like stable molecules. And then during various phases, when the radicals acquire some mobility in the ice, or also with alternative explanation, these radicals can react the one with each other in the ice and form all over the complex molecules that we have seen. So there are various stages to explain all these mechanisms, and I invite you again to read our chapter. And here I will just briefly mention some of these processes, especially for the cases where we do have recent achievements of the last years. Okay, let's start from the gas phase chemistry. As I said, these hydrides or simple molecules are somehow injected in the gas phase, and there they can react further. So in all the astrochemical models, there is an important set of a gas phase reaction, around 7,000, 8,000 reactions. So can we rely on these databases that we find around? Yes and no. Okay, most of the chemistry is there, but let's say there are problems because, as I said, not so many reactions have been investigated, and so all the other reactions have been introduced in the models with guessed parameters, relying on chemical intuition or analogy. But there are surprises. So there are surprises because, it's a complex stories, but I mean, you cannot easily guess, especially when the reactions are among neutrals. And so, for instance, after a recent inspection, we verified that there are actually more than 300 reactions included in the standard databases that cannot occur simply because they are endothermic. So there is not even enough energy to have them occurring. These reactions are there, and they can affect your model if you are playing with this. For instance, we have seen that the silicon chemistry is strongly affected by the reactions that we have now excluded from the models. Well, not only that, there were some reactions which should not be there, but there are also reactions which should be there and were not overlooked. For instance, recently we have verified that there is this nice chemical scheme where starting from ethanol, and ethanol can be formed on the icy mantle by the direct reaction of a radical C2H with the water molecules of ice itself. Starting from ethanol, we can produce glycolaldehyde, acetaldehyde, and acetic acid. And that's any kind of important message also, because we start from a larger molecule, ethanol, to go to smaller molecule like acetaldehyde. So that means that in the ice you can actually produce something which is more complex than the final outcome. And there is a nice correlation between some of these granddaughter species of ethanol in astronomical detection. Okay, since the time is terrible here, let me jump to other topics of that main plot that I showed to begin with. Thermal desorption. As I said, these molecules must come back to the gas phase somehow, both those formed in the prestellar core phase and also in the case, the more complex one formed in a subsequent step. So how do we account for this? Of course, the efficiency with which this molecule go back to the gas phase depends on the desorption rate coefficient, which is given by a pre-exponential factor, and then there is a term where you have the so-called binding energy, that is the energy, the interaction energy between the molecule and its substrate. Well, the point is that this value can be derived experimentally or also from quantum simulation, but for complex organic molecules, interstellar complex organic molecules, we do have a very few determinations so far. And so, but you do find a list of binding energy in the database, how they've been determined by simulating somehow the interaction of the molecule of interest with one water molecule and then a correction factor. So these are, of course, estimated value. When we compare them with those which have been really determined, especially with quantum simulation, well, we do see something interesting. This is actually not one binding energy of a specific molecule with water ice, because water ice is supposed to be amorphous up there. That means that it does have a structure, it's not a flat surface. And indeed, if you try to simulate more realistically that situation, you do find that the binding energy has a distribution, not only a single value. And depending on the site of the amorphous ice, where the molecule is actually absorbed. Not only that, The most realistic simulation of amorphous ice so far has been done with a set of 200 water molecules. And then when you consider something so complex as, for instance, an important molecule like ammonia, you see that not only you have a distribution, but it's a bimodal distribution. What does it mean? It means that there are a set of ammonia molecules which are adsorbed on water ice with a small binding energy, and that will be more easily released in the gas phase. You don't need to to go very high in temperature to have these molecules back to the gas phase. And this amount is sizable. Finally, there is one last point, not only the binding energy, maybe you're more familiar, some of you will be more familiar with this concept, but also this pre-exponential factor should be known and determined. And it has been estimated to be around 10 to 12 second minus 1, but in the cases where it has been determined for complex molecules, this is actually 6 orders of magnitude larger or 5 orders of magnitude larger. So there is still a lot to understand in this simple process as well. Very quickly to another point, which is at the heart of the grain-only chemistry, radical recombination on the ice. Why these processes have been thought to begin with? Well, we know from the gas phase reactions that if you have 2 unstable radicals, they can join together, forming a chemical bond and form a stable molecule. That can happen, of course, in the gas phase. The problem is that in a very rarefied medium like that of the interstellar medium, this process is not efficient because you need a 3-body collision. That means there is a third body colliding and taking away part of the energy liberated by the bond formation. This is what happens here in this room, for instance, if you have 2 radicals meeting each other, because here, of course, the density is much higher, is much larger. So the idea is that the same process can occur on the ice surface simply because the ice works as an energy dissipator. It's a perfect third body, the perfect third body. But this is not so simple, unfortunately, because radicals are interacting with the water molecules of the ice. Ice is not structureless matter. It's made up of molecules. And so the radicals can interact with the water molecules. They can actually react with them. This is typical of many radicals, like, for instance, cyano radical or C2H that we have seen reacting with the molecules in the of the ice. But not only reaction, they can also be any interaction. That means not really a reaction, but some interaction at the weak level that can change the reaction itself. It can introduce barriers. It can impede the reaction you are interested in. And very often there are competing reactions, and the water molecules of the ice are, in a way, conditioning the process. We have verified this for the case of the acetaldehyde. Acetaldehyde is supposed to be formed on ice by the recombination of the formyl and methyl radical. And this can occur indeed, but there is a competing process. So for the formyl radical, HCO can donate the hydrogen atom to the methyl radical that becomes methane. This is a very exothermic process indeed. And the 2 processes are in competition. So you can have the formation of acetaldehyde or the formation of carbon monoxide and methane. And water, the ice is in a way interacting with this competition. We have verified this in a more systematic approach, and actually you have seen that there are cases where radical recombination on ice works as you wish. In some other cases, there is a competition with other processes, and in some cases that process the competing process can actually be dominant or not. So you have to study each of these cases, and you cannot simply say, okay, let's play with domino or with Lego bricks, and then I join them as I wish. Okay, I'll give the word back to Claudio, but let me close by saying that what I mentioned is related to star-forming region, but keep in mind that if you use similar chemistry, you might have the same problem. So don't use acritically what you find in the models, because maybe the process you rely on might have problem.
Thank you very much, Nadia. And now, after having learned that chemistry is fantastic, is enlightening us, but it's also a mess, let's see what about the mess that we can find when we try to apply chemistry in through the phases of star forming process. Let's start our trip from the dense cloud. Let's start from the prestellar core to briefly introduce the guy here. Okay, of course, is a prestellar core that is deeply obscured. We are talking about very low temperatures, down to few Ks. We are talking about high densities, upper than 10 to the 4. We can briefly, let's see, we will see later why I cut this in 3. So if this is the radius, we can have a very inner part of the core where just molecules in the gas phase containing H and D, deuterium, can be there. And then there is a region going outside where carbon monoxide is depleted, but you can find, for instance, N2H+, that is a typical tracer. And then there is an external region where possibly you can find molecular gas. So one of the breakthrough since the last protostar and planets has been the detection of what we call icons in prestellar cores. Okay, so you can see several authors, several schools, several detections, and also an estimate of the abundances, 10 to the minus 11, 10 to the minus 9. So the question is why those species and where those species are located in this very cold gas. That is a very enlightening map that is comparing the black contours are for the continuum, that is picking where the black triangle is. And you can see that methanol has been observed, has been mapped, and is clearly spatially offset from the center, okay? So indeed, looks to resemble what I was saying before, that molecules so complex can be expected in the external layer of this cloud. The kind of cloud probably here because it's UV shielded as suggested by several authors. And yes, and so we have seen where they are, why they are. That's a mess, and that is a bit, I would say that it's still under debate, and what is probably, at least for us, the most explanation that can explain what we observe is that using VII and Herbst, the work of 13, followed by Nadia work of something like 2015, we have first a methanol non-thermal desorption, followed by gas phase reaction. That's a possibility. There are also possibilities with non-diffuse grain surface, but looks to fail, honestly, to reproduce what observed. So that was the first step. Now, the second step, now the golden region for icons that are protostars, okay? So indeed, we have the old but still valid sentence introducing hot Corinos by Cecilia. That is the inner region inside the 100 AU where the temperature is high enough, more than 100 Kelvin, to evaporate the mantle grains, okay? So to enrich the gas phase. And you can see here the inner part that is inside 100 AU. And what's outside, we could have regions where carbon chains are dominating because the methane can sublimate at lower temperatures, okay? So it is true, yes, it is true because there are plenty of large programs tracing the chemical composition of hot Corinos, of the inner region of the stars. We can see here the classical IRA 16293 that has been a great large program by Jesse Jorgensen, PILS. And you can see a forest of lines, as well as a forest of lines can be observed, for instance, in a more evolved SVS 13A, that is class 1 object, 10 to the 5, roughly. You can see also one of the outputs of the large program Faust, that is here observing again a class 1 object, and you can see plenty of icons. So problem solved? Not exactly, because when we are going to be out of the best friends, okay? So the classical 3, 4, 5 objects super studied, we have to understand what's the statistics here, okay? So we could, a possibility is to compare the peaches and oranges projects that are, why I compared that? I compared that because they are observed at the same roughly frequency with the same instrument, ALMA, and with a similar spatial resolution. And we will see that there are difference. Of course, statistics is, let me say, ridiculous. We are friends, so no one is going to. So we need really high numbers. But it looks that in Orion, with respect to Perseus, there are less hot corinos, possibly because a larger UV field, okay? And then there are two effects that are affecting the detection or not. It's the problem of ALMA. ALMA is so good, is observing a very high resolution, is observing a very high frequencies that is touching the problems introduced by the opacity of dust, okay, around the star. So you can start to miss emission because the continuum emission is killing, from the radiative point of view, the lines, okay? And on the other hand, you could observe, we will see later, also an onion structure because of different binding energies. So the higher the frequencies, the higher the opacity, so we see less lines, and the higher the binding energy, the closer you have to go to observe that molecules, but where you have dust opacity effect. And then the catastrophe is that you can also miss hot corinos with ALMA. Here you can see, for instance, IRAS for A1 and 2, a binary that is in continuum with ALMA, and with Firmamid, wow, there is just one hot corino. What about this? It's missing. Different natures are not coeval. No, it's there. That's methanol. If you go to observe at a centimeter of wavelengths, where dust opacity is less affecting the line, you can see there. So be careful, because we can miss hot corinos with ALMA, and we have to be prepared to complement ALMA also with centimeter observation. So now a brief tour in the jet. We say that, you know that of course jets are ejected and are creating from protostar and are creating shocks. Why are important shocks? Because of three reasons. The first one is that are far from the protostar, so we can forget about effects due to the protostar. The second one is that the dust is destroyed, is sputtered, so everything is enriching the gas phase. Third effect is that we know an estimate of the kinematical age. Of course, it's not so easy, but at least we have a possibility. So the old protostar and planets, fantastic results. We're introducing L1157 laboratory, where there is a star driving a very chemically rich. Chemically rich, we were saying 20 years ago, because we were observing SIO, we were observing methanol. But now, indeed, in the last 10 years, we saw that we can observe everything there. So shocks are ICOMS factories. And for that, it's important to do an anatomy of this. So let me introduce this. So this is the same source of before. Here is a bow shock that is indeed made, but several shocks occurring. And you can see when you go interferometry, in this case with Noema, that every molecule is peaking here and is peaking here and there. So there is a different a dichotomy, right? Because are testing different physical conditions. And the point here to get that high velocity SIO is peaking here. So this is the youngest within B1, between this region, shock event. So what, Claudio? Well, you see here that there is a dichotomy between acetaldehyde and formamide. Formamide in color, acetaldehyde in contours. And you can see there is a dichotomy. Why there is a dichotomy? If everything is expected in principle to be sputtered from mantles when the shock arrive. So we think a possibility, an idea, is that there is gas phase at work. Here there is a delay in time. So it looks that we need a bit of time to produce formamide, so we try with gas, and it works. Is the unique solution? No. But it is a possible solution. The last step towards us, towards the solar system, is the protoplanetary disk. I'm not going to talk in details about that, because of course there are plenty of chapters speaking about these steps, but you know that from the molecular point of view, you can observe the molecules only in the warm molecular layer, where the dust is warmer enough to observe icons. So you can easily image that there is a density and temperature gradients horizontally and vertically. So what we are observing here, we start to observe something. We start to observe, well, the first pioneeristic of Catherine Walsh observed methanol there. She was the first one, pushing us to look for methanol also in other sources. We have here the class 1 that you can see that the detection is not so clear as before, okay? Because it is really a question also of column density expected in the disk. And then there is, for instance, MAPS that is giving us plenty of CA3CN and HCA3N. It looks then that N-bearing species are more easily observed towards protoplanetary disks. Is this true? Is this due to binding energy, as we say before, that the binding energies of nitrogen-bearing species can be higher? Matter of debate. We have two other possibilities to bypass this problem: going to very high luminosity object, Oberg, or what we say before, bursting disk. So you can see here a lot of species. So species are there, no problem. And the last example is HH212. That is a unique case because it's the unique protostellar disk observed with a resolution in many molecules and in continuum with a resolution of HAU, so really solar system scale. And you can see that if you compare lines of methanol and formamide with the same excitation, so it's not a problem of excitation, formamide, the red contours here, is more compact than methanol. And this is in agreement again with the fact that formamide is associated with a higher binding energies range, with all the caveats said by Nadia before. So, to conclude, if we start, statistics is very low. To conclude, there is, if we compare, for instance, dimethyl ether with methylformate, why those? Because methanol can be affected by opacity effects. So we see that class 0, class 1, and prestellar are within a factor of 10 in the same range. And if we go with comets, because now we have to do a huge jump, 10 to the 4, 10 to the 5, 10 to the 6, but then we are at 10 to the 9. Okay, so it's really huge step. We can just have a look with comets, and with comets, the comparison is not so bad. It looks that there is a factor 10 of differences, but again, could be here. In this case, we have to use methanol. And so it looks that chemistry is always the same. So these are the conclusions, perfect. Just that chemistry looks the same from prestellar cores to hot coronas to protoplanetary disks, and even maybe in comets. But more statistics is clearly needed. And this is the last slide to tell that, of course, next tools are needed. For instance, the AWST will tell us a lot on grains. Centimeter interferometers will be fantastic solution, and be careful with chemistry, because if you use badly, we use badly chemistry, we can badly obtain bad results. Thank you very much for your attention.
Thank you for an excellent summary. It's a time for questions. Yeah, let's start in the middle of the microphone.
Hi, Claudio. Hi, Nadia. Sometimes in many Protostars meetings, you hear about this concept of chemical clocks. I think we heard about it earlier this week also. And in contrast, there is a school of thought that says, well, abundances are sort of similar for many sources. So that suggests that that clock somehow doesn't work. I was curious, what is your view on the chemical clock concept?
Okay, I can give my answer. Okay, yes. I was a fan of chemical clocks. I started in the 90s playing with a lot of people on sulfur and the classical, for instance, H2S, SO, SO2 route. I have to say that with time I'm a bit more skeptical, because it looks that what we observe is not just a question about the molecule, if it is there or it is not. It is related also where we observe this, how much we are affected by absorption, how much we are touched by opacity of the continuum behind. So around protostars, it's a really nice effort, but I'm not so optimistic. Another case is shocks. That because shocks there, you have a bit, the time, the kinematical time, but is a kinematical time, of course, is associated with several problems due to assuming that a velocity was always the same. So really, when you do distance and velocity, you derive a time. I would like to, I like more spatial anticorrelation. If we observe something like that, clearly spatial anticorrelation and not factored within, in an order of magnitude, then we can do something maybe.
Great to hear. Thank you.
Question from the right.
This one. So, Mordecai Maklo, AMNH. I have a philosophical question, I'm afraid, which is, or maybe it's just a practical one of logistics. How do you get complex reduced carbon molecules from interstellar or even disk regions onto planets without destroying them during accretion?
Nadia, if you
But
want, yes.
this is an interesting question, of course. So the basic idea is that there are, let's say, carriers that can bring these molecules that survived far away from the center, from the new star. These carriers can be comets, meteorites, asteroids. We do see these molecules in those small bodies. So the possibility is that these molecules are preserved in the outer bound of the newly formed solar system, and then they are brought somehow by these carriers to the planets. And indeed, we do see these reduced compounds in meteorites, and meteorites which landed, so that arrived here. But let me just add a little point. As I said, I'm a chemist, and of course I'm used to, to work in the lab and so on. But when you do see formamide or glycolaldehyde, these molecules that do have a prebiotic potential, because they can really evolve into real precursors of biomolecules, let's say, and when you see them in these very far objects, that means that you have a huge amount of them to see them from here remotely by radio astronomy. Of course, not all of them will be inherited in the small bodies or large bodies of the solar system, but really we are dealing with a huge amount of this. And if you consider all the biomass, if you compute the mass of all living entities on Earth now, it's a little amount. It's less than 1 billionth of the total mass of the planet. So you really need to inseminate, with a small amount of reduced carbon.
But you have to concentrate it.
Concentrated, yes, of course. But also keep in mind that reduced carbon is only in living entities, because as soon as carbon is out of living entities, it is immediately converted into CO2 or carbonate. Well, actually, most of inorganic carbon on Earth is in the lithosphere as calcium carbonate, magnesium carbonate, okay? And then, of course, we have some CO2 in air, and we know because it's causing a lot of problems. But most of our oxidized carbon is in the lithosphere now.
Thank you.
Thanks to life, because these are sedimentary rocks. Okay.
Let me just comment also, sorry, I just add in the same context that indeed the comparison with the object of the solar systems like outer solar objects and the comets is just started because we need terrible need to have statistics.
Okay, let's have a question from here.
Hi, Adam Ginsberg from the University of Florida. So you showed that shocks are calm factories. Those shocked regions are then getting mixed back into the molecular cloud, and so presumably they're seeding the initial conditions with already rich with complex organic molecules, but the chemistry networks are all starting from pristine conditions. Do you have a sense of what effect starting with complex molecules already, but before you get to the pre-stellar phase, might have?
It's a very good question, and is not easy to answer because it depends where the shocks occurs. We have two kinds of shocks, indeed. One is not shown here, but is described in the chapter and has been introduced by our Japanese colleague, for instance, Naomi Sakai. That is the accretion shock, where the material from the infall envelope need to lose energy to join the accretion shock, the accretion disk, the rotating disk. So we have very small shocks, very small velocity shocks, like 1 kilometer per second, that are not the 10 kilometer per second shocks caused by the jet. And also there we can have complex organic species. So we can have species really in the inner 50 AU, as well as at 1 parsec of different offset from the star. I would say that, in the context of your questions, it's more important what the fate of the organics created at 50 AU. But it's not clear so far. It's an interesting topic.
Okay, let's have a question from the back. Yeah.
Lauren Weiss, University of Notre Dame. I apologize, I haven't taken a chemistry class since high school, so this might be a rather naive follow-up to Adam Ginsberg's question. So if the binding energy that's necessary for creating these complex molecules is important, and you can have high binding energy with, say, these variable or episodic accretion events, or these shocks when a molecular cloud is collapsing and creating an accretion disk, What about shocks or energetic events from elsewhere in the galaxy? Things like supernovae or neutron star mergers. Could these very short timescale but very high energy events cascade in some way that it at some point produces some energy profile and temperature profile conducive to the formation of complex molecules?
Thank you. Do you want to go? Yes.
Just a little remark, binding energy is not important to form, but to release in the gas phase where we mostly see these species. And of course, there are many processes that can lead molecules back from the ice mantle to the gas phase, and all of them are listed in the book chapter. And in principle, everything which is providing energy, of course, helps in make them sublimate and having them in the gas phase. And the question about binding energy and the distribution is that some of them will be retained more effectively by the substrate, some other will be released more easily. So this is just to explain that you might have this sublimation also in regions where you don't expect it. But of course, every time you provide some form of energy, you promote sublimation.
Okay, then let's have a question from the right back and left back.
Álvaro Sánchez Monge from Institute of Space Sciences in Spain. So thanks for the talk. I have a question. So if you can comment a bit more on the possible mechanisms that allow the detection of COMS in cold and quiescent cores, where thermal desorption or shocks seem to not be dominant. So how can we detect them in these places?
Well, the shortest answer is in the gas phase. You synthesize them in the gas phase. Well, but of course, as I said, you might have the release. So for instance, there are mechanisms which are described in the chapter according to which the reaction itself on the ice, which is liberating energy, can provide some energy to sublimate the compound itself. So it's a so-called chemical desorption. It's a little bit difficult to quantify, but there are evidence for some cases with quantum simulation where you do see that the molecules is formed and the energy liberated is enough to let sublimate. For instance, that's true for the recombination of atomic hydrogen into a hydrogen molecule. So the energy is enough to let the molecule formed leave. In that case, molecular hydrogen has a small binding energy, so that means that energy liberated, which is a lot, can make this process happen. But there have been estimates, according to some estimate, roughly 1% of the molecules formed with a large exothermicity can be liberated by the ice, if, of course, they form, because in very cold regions, the mobility on the ice will be very small, so you need non-diffusive processes. All of them are described in the book chapter. Unfortunately, I cannot give all the details here.
Thank you.
In any case, just to comment, I guess in the chapter where the state of the art, we hope, of what the comparison between chemists and astronomers, observations, models, and quantum simulations, we are far to understand what's going on in any single step leading to us.
Okay, last question from the side.
Thomas Henning from Heidelberg. I actually have a comment on your chemistry part. You mostly talked about radical reactions, but in these protected areas we just talked about, you do not have UV radiation. And I just wanted to point out that there is a new class of chemistry going on at low temperatures, which is actually neutral reactions, which do not need any activation energy. That has been demonstrated in a number of laboratories, and I think this is an important part of the game.
I'm not sure I understood what you mean. If you mean a neutral reaction in the gas phase, I totally agree with you.
No, on the surface of the ice.
On the surface, well, the question, yes, of course, you have to verify case by case. So in some cases, the interaction with the water molecules can make the reaction less efficient. In some other cases, there is no problem, and they can occur, of course, yes. There are normally, actually, radical recombination reactions are barrierless.
And my point was just that you don't need radicals.
So you mean two closed shell species reacting on two closed shell species?
If you take atomic carbon, ammonia, and water, it will react.
Atomic carbon is not a closed shell species, yes. In that case, of course. I mentioned actually that you can have the reaction of radicals directly with the components of the ice. ammonia also, yeah.
Yeah,
Of course.
our time's up.
The final point, sorry, just 10 seconds, is that of course there are not, is not a war that I don't want to say this word between gas versus grain surface. It's obvious that grain surface is a must in space. The question is, are we thinking that grain surface is enough to explain everything, or do we need also gas phase chemistry? That is the point.
Yeah, we have to move to next. Let's thank our speakers again.